This is section 11.3, vectors and their applications. First of all, I'd like to talk about what a vector is, so we can get started with that concept. It's something that has both a magnitude and a direction. So, first of all, let's talk about what a scalar is, because that leads us in that direction well. A scalar is a magnitude. It's the size of a force, like 45 pounds. So the scalar would be, for example, the weight of an object. A vector quantity is something that has both magnitude and direction. For example, 50 miles per hour is a scalar, but if you say 50 miles per hour east, that's a vector quantity. Now, typically, when I write a vector, we'll use the one notation that we can employ in handwritten notation easily. Is if we have a vector that goes from point O to point P, then the notation that we're going to use for that is this symbol over the vector, meaning it goes from O to P. In printed things, you'll see that they use a bold type when it's typed out, but when it's handwritten, the only way we can do that consistently and understandably always the same is with that arrow on top, indicating that we have a vector. The letter O is called the initial point. The second letter P is called the terminal point. And there is the possibility of a vector that goes from P to O, but they are not the same. They have opposite directions. So if I can make this the same length, and it's supposed to be parallel, this one starts at P and ends at O, and so this would be vector PO. So the order in which you write those letters is important. The first letter is always the initial point. The second letter is always the terminal point. They do have the same magnitude. That's what I was trying to draw. I think I made one of them a little bit longer than the other, but pretend like I was able to make those exactly the same length. And if they were exactly the same length, then you could say they have the same magnitude, but opposite directions. Okay, so we're going to talk about vectors being equal, and they're equal if and only if they have exactly the same magnitude and direction. So if I were to draw another vector over here, and I'm going to try to make it look like it's the same magnitude and direction as OP, and let's say this one is AB, then we could say that vector OP is equal to vector AB. And again, we're assuming that my drawings are perfect, which of course they're not. So I hope you're looking at good drawings in the notes that I've posted. Now, to add two vectors is the next thing. So if I wanted to take a vector called A, and sometimes we give them a single letter name, so we're not naming the initial point nor the terminal point. We're just saying this is the name of this vector. And that'll happen quite frequently. If we have a vector A, let's say it looks like this, and a vector B, and let's say it looks like this. If I wanted to add vector A, by the way, we still have that arrow over the name of the vector to show that it's a vector. Over B, I should have the arrow as well. So vector A plus vector B. There are basically two ways to add. The first of which is what I might sometimes call the head to tail method. If I were to draw A again, and then start drawing B where A's terminal point is, pick up right there and start drawing B, and then the resultant vector will go from the initial point of our first vector A to the terminal point of our second vector B, like that, and that is the new vector, vector A plus vector B. And again, the term I use for that is resultant. It's the result of adding the vectors. It's called the resultant vector. So again, so that this is clearly labeled, this was vector A, and this is vector B. The other way to add vectors, oh, and by the way, that method I just talked about, the head to tail method, you can add as many vectors as you want. You just keep starting the next one where the last one left off, and then when you add another one, just start the next one where that one left off, and your final resultant vector will go from the very first initial point to the very last terminal point. And that's kind of the strength of that technique. And that's the one I tend to like myself. Okay, so now if I were to draw vector A over here, pretend like that's vector A. Not sure I got the direction and magnitude exactly right. At any rate, if I were to make the initial point for my other vector the same point as the initial point for vector A, then if I were to draw in a parallelogram using those two as the sides of a parallelogram, of course, you know, parallelograms have opposite sides that are parallel and congruent, and so I would draw parallels to the two vectors I have, and they should be exactly the same length as the two vectors that I have. And of course, perfection here is wanting because it's awfully hard to draw this freehand perfectly. Anyway, the resultant vector will go from the initial points that you started with and go along the diagonal to the other vertex across from the vertex where you started. And that is vector A plus vector B as well. And you'll notice that my two vectors, although maybe not perfectly the same, they're at least supposed to be vectors that have the same magnitude and direction. So those are the two major ways to add vectors. As you read on the next page, vector addition is commutative. Vector A plus vector B is the same thing as vector B plus vector A. And again, that terminology that's called the resultant of A and B is when you add the two vectors. For every vector V, there is an opposite V vector such that vector V plus opposite of vector V is equal to 0, the 0 vector. Let me write that in notation that we need to make sure that you're getting. See all those bold-faced things? If I were writing vector V, it would be this. And if I were writing the opposite of vector V, it would look like this. And the 0 vector looks like that. It's actually a vector whose magnitude is 0 and direction is nothing. There is no direction. It could point any way at all that you want at all. Now, so if this is vector V, then this would be the opposite of vector V. And there are other vectors on this page that are actually opposites. Vector OP is the opposite of vector PO. So first vectors we talked about. Same direction of movement but opposite. I'm sorry, like the angle that creates to the horizontal that creates the direction. They're at the same angle but pointing opposite directions, and they have the same magnitude. Now, a scalar product is what you get when you take any number like k. Notice k is a number, so it doesn't get a vector symbol, and multiply it by a vector. Well, as you know, multiplication comes from repeated addition, so that would be vector v added to itself for a total of k vectors that are being added. And so if I had, for example, 3 times vector v, that's going to be vector v plus vector v plus vector v. And of course, the resultant starts here and ends where the last one ended. And so this is the vector 3v in that color. K can be any real number. The magnitude of the resultant will be the absolute value of k. Because magnitude is a size, it's got to be positive. And if you were doing negative 4v, for example, that would go something like this. Pretend like that's exactly 4 times the length of v, but pointing in the opposite direction. And its magnitude would be the absolute value of negative 4. So its magnitude is 4, its length is 4. Okay. And if k is negative, it will point in the opposite direction from the original vector. Then there are several pictures there of u, and then what twice u would look like, what 3/2 u would look like, what 1/2 of u would look like, and what negative 2u would look like. Now, one of the standard things that you can do with vectors is you can move them wherever you want. It's like if it's representing a force, you can draw that force like if it's a wind hitting an airplane. The force of that wind can be drawn to anywhere on the plane you want, because it's going to have that same direction and magnitude everywhere on the plane. So you can just move that around wherever you want it to be. So a lot of times what we do is we put a vector in standard position, which means that its initial point is at the origin. So assuming this is the xy plane and each mark on my axis represents 1, then I could have a vector v like this one that starts at the origin and goes someplace from there. Like, let's say it's that vector right there. This is vector v. A position vector u with endpoint AB is written as vector u equals that angle bracket, pointing bracket, A, comma, B, pointing bracket the other way. So this vector right here that I've drawn, vector v, is equal to pointing bracket 1, comma, 3, pointing bracket, because it terminates at the point 1, 3. So calling its location or its name by the ending point is valid, because if we make all of them start at the origin, the terminal point is sufficient to make it a unique vector. And what we're going to call the A part of that, so generically for vector u, this is going to be AB in those pointy brackets. A is called the horizontal component. of the vector. And B is called the vertical component of the vector. Okay, so what is the horizontal component of vector v that I drew in the plane? It's 1. What's the vertical component of vector v? That's 3. Okay. So if we talk about the horizontal and component numbers as an identification for the vector, that's what we call component form. Now, if you think about something in standard position like that, like 1, 3, how would we find its magnitude? Well, the magnitude, of course, is the length of that vector. And so it's obviously the distance between the terminal point and the initial point. And we know the distance formula is always going to be x sub 2, so 1, minus x sub 1, always 0 if we're using component form. One of the points is the origin, squared, plus y sub 2, which is 3, minus y sub 1, again 0 because it's the origin, squared. And so it's actually sufficient to write a squared plus b squared because you'll be subtracting 0. So in general, I'll put that over here, the magnitude of a vector is the square root of a squared plus b squared. And in this particular case, that's the square root of 10. Now the symbol for the magnitude of a vector is looks like absolute value. It's not absolute value, but it sure reminds me of it. You write the name of the vector and put these vertical bars around it, and that means magnitude of vector u. Actually, that was vector v just now. So let me fix that, because that was vector v. So this is the magnitude of vector v. And so in general, if you have a vector u that has component form AB, then the magnitude of vector u is the square root of a squared plus b squared. So that's a formula you're going to want to make sure that you've committed to memory. That's something you need to know. All right. Now the direction angle, oops, I probably shouldn't have moved up that far. The direction angle is the same angle we're used to talking about, measured from the positive x-axis. So let's say that that's angle theta. The A part is what we would normally call x, and the B part is what we normally call y. And what is the relationship between x and y and theta? Well, of course, you know it already. It's the tangent of angle theta is y over x. So using the terminology for vectors, that's going to be, instead of y, b, over, instead of x, a. And of course, a can't be 0 because you can't divide by 0. Okay. And that'll give you the direction angle, theta. That's another bit of vocabulary. And so that's how you find it. So those are important concepts. All right. All right, so let's do an example. Let's say that vector u is one whose component form is 3, -2. And of course, if we wanted to graph it, then that would not be a difficult task, because in component form, it's just telling you where the terminal point is for the vector, because the initial point will always be at the origin. So we'll go to 3, -2, and then draw the vector like that. So there's vector u. Okay, so the question here is going to use both of those formulas. It says, first of all, what's the magnitude of u? So we'll do that first. The magnitude of u is, according to the formula, the square root of a, which is 3, squared, plus b squared, which is the square of -2. 9 plus 4 is 13, so the magnitude is square root of 13. Okay, then the tangent of theta is b, which is -2, over a, which is 3. And so to find theta, we would find the tangent inverse of -2/3. And using our calculators, we get an answer of -33.7 degrees, assuming we want degrees for that. And in fact, let's just go ahead and say that direction angles in this unit, let's just go with degree measures. That way we'll have a thing to go with. So that is the angle if we wanted a negative angle. A lot of times, however, when we're writing the direction angle, we'll want an angle between 0 and 360 degrees. So let me write that up here. Generally speaking, we want the direction angle to be between 0 and 360 degrees. Of course, -33.7 degrees is coterminal to our answer, but it's not what we want. So to get the correct answer, we're going to add 360 degrees to take it all the way around the circle. And that gives us approximately 326.3 degrees. Okay. So let's take a look at this a little bit more. We know that, sorry, I couldn't find my pen. There it is. We know that when we have a triangle, let's go with that. Let's go with if we have a triangle, and the magnitude of this hypotenuse is the magnitude of vector u. So this is representing vector u, and its length is the magnitude. And if this is theta right there, how will we represent this horizontal component A using those two? If those two were known, the magnitude of the vector u and the direction angle, how would I express A from that? Well, with a right triangle, we know that the adjacent and hypotenuse are related to the angle by the cosine function. And so we know that cosine of theta is adjacent A over hypotenuse, magnitude of u. And if you solve that for A by multiplying both sides by the magnitude of u, A will be the magnitude of u times cosine theta. Using similar reasoning, we can find B, because that's the opposite side from the angle, and of course the magnitude of u is still the hypotenuse. And we know that the relationship there is that the sine of theta is opposite over hypotenuse, and solving for B gives us the magnitude of u times the sine of theta. So those are another couple of formulas that I expect that you need to commit to memory. The horizontal and vertical components A and B can be found by multiplying the magnitude of the vector u by either cosine of theta for the horizontal component or by sine of theta for the vertical component. And so what that results in is this following statement, that the vector u, which in component form is AB, can be found if the magnitude and direction angle are known by using the formulas given, and this will be the magnitude of vector u times the cosine of theta to get A, comma, magnitude of u times the sine of theta to get B. All right, so that's also worthy of your attention. And it's just a putting together of the ideas above. So this circle doesn't encircle anything brand new. It's just kind of putting the ideas together. All right, so moving on. Example, vector w in the figure has a magnitude of 25.0 and a direction angle of 41.7 degrees. So let me write that down. The magnitude of vector w that's shown is 25.0, and the direction angle is given to be 41.7 degrees. Okay, find the horizontal and vertical components. Well, the horizontal component is going to be the magnitude of w, which is 25.0, times the cosine of the direction angle, which is 41.7 degrees. And so A is about 18.7. And the vertical component B is going to be the magnitude 25.0 times the sine of the direction angle, and that ends up giving us about 16.6. And so therefore we can conclude that vector w in component form is 18.7 comma 16.6. And of course, I've rounded those to the nearest tenth. You probably realize that already. Okay, so the next example, you're looking at a figure that has 3 different vectors, and we're supposed to write each vector in the form, in the component form. So looking at u, it appears that u has a magnitude of 5, and vector u has a direction angle of 60 degrees. Kind of color coded there, it's in blue, so it makes it easy to see. And the vertical component will be 5 times the sine. of 60 degrees. Now these are trig values that we know without resorting to a calculator. So the cosine of 60 degrees is 1/2, and the sine of 60 degrees is square root of 3/2. And so the component form, our final answer is 5/2, comma, 5 square roots of 3/2. Okay, now let's look at vector v. By the way, the names of vectors that people like to use are u and v and w are pretty common. Just saying, it's kind of an important concept. All right, so the magnitude of vector v appears to be 2, and the direction angle is 180 degrees. It's in red. And so 2 sine of 180 degrees will be the vertical component. Cosine of 180 degrees is -1. The sine of 180 degrees is 0. And so that vector is -2, 0. And then w. By the way, that last one, you could tell that that terminated at the point -2, 0, right? So those calculations are meant to show you that if you go at this route, it always works, even for the ones that are easy. All right, for w, the magnitude is 6. The direction angle is 280 degrees. That's not one of those angles that we know how to find nice answers for. So we are going to resort to using our calculators here. And let's round to 4 decimal places. So the magnitude times cosine theta, comma, magnitude times sine of theta is what we just did. When you type those in the calculator, you should get that the horizontal component is 1.0419. And the vertical component is about -5.9088. Okay. So if you're going to add vectors using the parallelogram method, and if we end up using parallelograms for any other of our problems we're going to be dealing with, hint, hint, yes, we'll need these. The next page has properties of parallelograms. These are things that you probably already know. Parallelogram is a 4-sided figure, hence a quadrilateral, whose opposite sides are parallel. I think I already mentioned that earlier. 2. The opposite sides and opposite angles of a parallelogram are equal. I think I mentioned opposite sides, but I didn't mention opposite angles. So let me draw a non-perfect parallelogram. And that means this side and this side are congruent. This side and this side are congruent. This angle and this angle are congruent. This angle and this angle are congruent. And the sides, opposite sides are parallel. And adjacent angles, that is the one that's 1 mark and the one that's 2 mark are adjacent to each other, are always supplementary. So if this is angle A and this is angle B, angle A plus, or the measure of angle A plus the measure of angle B, because it's a parallelogram and those are adjacent, will always be 180 degrees. So they're supplementary. I hate to draw into that same one, so I'm going to make another parallelogram. Pretend like that's a perfect parallelogram. Thanks for pretending. If I were to draw those diagonals in, there's one of the diagonals, and there's the other diagonal. And what's true about these is that the diagonals bisect each other, meaning this length is the same as that length. And the point of intersection is where we're splitting it into the two. And this length is the same as that length. Notice that those lengths are not the same. The one that's marked with one hash mark, and the one with two, those are not the same most of the time. And so we'll say that the diagonals bisect each other, but they do not necessarily bisect and get equal. What am I trying to say? They bisect each other, but they don't create necessarily equal lengths from vertex to the point of intersection. The other thing I want to say is that the diagonals don't necessarily bisect the vertex and the angles of the parallelogram. So notice, for example, the angle right here and the angle right here are not the same angle size. And so the angle in the parallelogram is not bisected necessarily. It's not bisected. It can, but it doesn't have to bisect the angle there. Alrighty, so those are some of the properties of parallelograms that we may need in some of the problems that we encounter. Alright, so let's do an example. Two forces of 15 and 22 newtons act on a point in the plane. If the angle between the forces is 100 degrees, find the magnitude of the resultant force. So if we look at a picture of what I just described, you'll have one vector, let's say it's that one, that has magnitude 15. And let's say this is point P and this is point Q. And you have another vector, let's say this one, and this will be point S. And the magnitude of this vector is 22. And the angle between them is 100 degrees. Okay? The question is that we're supposed to find the magnitude of the resultant force. All right. So with point P being the common initial point for those, that means we're using the parallelogram method to add them. That's what they are assuming we're doing. So I'm going to draw in a parallelogram using those two vectors as guides for drawing the rest of the parallelogram. And the resultant will go from the initial point, the common initial point, to the opposite angle, so along the diagonal. That's the resultant there in pink. And because of the supplementary nature of the adjacent angles, the angle at P is 100 and the angle at Q therefore has to be how big? Well, since they're supplementary, that angle has to be 80 degrees. Okay. And so, and because of the properties of parallelograms, I could also say that this side has length 22 as well. And of course, the question is, what is the magnitude of this vector here? Let's call that vector V. And our question is, what is its magnitude? Okay. So if you notice, by drawing in that diagonal, we've created a triangle. I know two sides of that triangle, 15 and 22, and I know the angle between them, 80 degrees. And so, how do we solve for the other side? As I've said many times, everything you've ever learned in this course and prior courses, you get to use again. So if we're going to try to solve this triangle, and we have side angle side, what allows us to find the missing side? Well, the missing side, by the law of cosines, is such that the square of that length is equal to the side length of one of the known sides squared plus the other side squared minus 2 times the product of those two sides that we just mentioned times the cosine of 80 degrees. So if you take the square root of that mess on the right side, you end up getting that the magnitude is about 24. And since this is a word problem, you might want to reread it. And am I done? No. The magnitude has a unit of measurement. The other two lengths were in newtons, and so this magnitude would also be in newtons. All right, on the next page, there are some vector operations, some things that you should learn how to do. They're very easy. I'm going to copy them down here. If you have component forms for your vectors, the addition of them is really simple to do. Basically, think of adding the two horizontal components together to get the new horizontal component, and add the vertical components together to get the new vertical component. If you have a scalar multiple of a vector in component form, you can think of that as distribution. You're going to multiply the scalar times the horizontal component and multiply the scalar by the vertical component. If U is in component form A1, comma A2, and that would imply that the opposite of U, which is -1 times our vector, will be the opposite of A sub 1, comma the opposite of A sub 2. So again, you just distribute. And if we have one vector in component form minus another one in component form, then you can think of that subtraction as addition of the opposite. So I'm going to change this into addition of the opposite of CD. And then, just like in the last line, that second thing will become, when you distribute it in, negative C plus D. Oh, what am I saying plus for? Sorry, getting ahead of myself. Negative C comma negative D, which is A plus the opposite of C, comma B plus the opposite of D, and of course the addition of the opposite is more simply going to be A minus C, comma B minus D. And that's a lot of steps. And basically what I've just done is I've done a proof of how you subtract vectors in component form. Just like addition, you subtract the horizontal components, comma, subtract the vertical components in the same order in which they appear. So it's A minus C, not C minus A. So that's kind of a proof of why that's true. So let's do an example. Let's say vector U is in component form -2, 1, and V in component form is 4, 3. So we're supposed to find several different things, so let's find them. First, they want us to do u plus v. So that's negative 2 comma 1 plus 4 comma 3, which is negative 2 plus 4 comma 1 plus 3. And that simplifies to be 2 comma 4. All right. In part B, we're supposed to find the opposite of 2u. So that's going to be negative 2 times negative 2 comma 1, which is negative 2 times negative 2 comma negative 2 times 1, which is 4 negative 2. All right, before we get away from those two examples, I'd like to draw pictures of what those look like. So that we always have an idea of what we're getting physically with the addition or subtraction or scalar multiple or what have you of vectors. So vector v starts at 0, 0, terminates at negative 2, 1. So I'm doing vector v in pink. No, I'm sorry, vector u is in pink. And vector v is 4, 3. 3, 4, 3. And the resultant of u plus v is 2, 4. And now that you see that, can you envision the parallelogram that could have been drawn and we just drew the diagonal? You see it? I'll kind of jot it in. I don't know if you can see that. It's real faint, kind of on purpose. I'll make it too bold. So the component addition actually gives us the correct answer. That's what I wanted you to see, is that that's working. The other one, x, y, okay, so again, vector u I'm going to do in pink, terminates at negative 2, 1. And the resultant is 4, 2. So 4, negative 2, excuse me, 1, 2, 3, 4, negative 2. And that's in the same line as the pink one, but it's twice as long and in the opposite direction. So that's supposed to give you some confidence, especially if my drawings were a little bit better, that the component formulas that we learned above actually do work. Okay, let's do the next one. 3u minus 2v. That's 3 times negative 2, 1 minus 2 times 4, 3 so that's negative 6 comma 3 minus 8 comma 6. And let's see, negative 6 minus 8 is negative 14. And 3 minus 6 is negative 3. By the way, this problem I'm doing a lot like how I want you to do them. The first problems where I showed every little step is, showing every little step. But I expect that you can do some of that more quickly. And this is a pretty good example of what I would want you to show as far as your work is concerned. Okay, so next we're going to turn to something called a unit vector. Oh, we're going to go to the next recording to do that. This is a good place to stop.